Okay, we're starting on the notes for 3A in the Math 4 course. And I thought you would want to hit pause a second and read this. This makes a fairly startling statement as far as I'm concerned. All right, today we will be talking about rules of exponents and properties of logarithms. We are going to spend some time with the same base method just to refresh your memory on that as far as solving problems. And we're going to get the basic converting logarithms to exponents and exponents to logarithms. A lot of this is a review from Math 3. We're going to be there for the first one or two sections here before we start digging into some new material about logarithms. So, all right, first of all, let's refresh our memory on the rules. If I am saying x to the a times x to the b, I am going to add those exponents. If I'm dividing, I am going to subtract those exponents. If I'm raising a power to a power, I am going to multiply those two. And if I have this set up, then I am distributing x to the a times y to the a. Now, for the power of a quotient, I'm still distributing, but it's still going to look like x to the a on top and y to the a on the bottom. And of course, anything raised to 0 is plain old 1. And two other rules that we learned along the way: if we have a negative exponent, it is as if I had put it underneath with a positive exponent. And this guy, the guy on the bottom is the root, and that is the exponent. So we're going to say the b root of x to the a. Now this would be like saying x to the 2/3 would be the same thing as putting the 3 in the pocket and leaving the 2 there. And we actually will run across some problems where, and sometimes it's beneficial that when something is given to you as a radical, to change it into something that has a fraction for an exponent, what we call a rational exponent. And you're able to play with it algebraically as a fraction, a lot easier than trying to play with the radical. All right, let's see what happens here. I've got a big 2 times a big 2, which gives me a big 4. X to the 3 times x to the negative 1, I'm going to add those. 3 minus 1 is x to the 2. And then y to the negative 3 times y to the positive 3. Negative 3 plus 3 gives me 0, which, of course, anything raised to the 0 becomes 1, and I might as well just leave it out. So we get over here, and we say big 4 times big 3 gives me big 12. A to the 3rd times a to the negative 4 is going to give me an a to the negative 1. 3 minus 4 is negative 1. B squared times b to the negative 3rd. 2 minus 3 is a negative 1. Now, they didn't say so here, but a lot of times you'll have them, you'll see them ask you to leave the exponents as positive numbers. And that's what it would look like if you did that. All right, now here, by the time we finish distributing that 4 on the outside, let's see, 4 to the 1 is 4, 4 to the 2 is 16, 4 to the 3 is 64, 4 to the 4 is 256, and r to the 0 times 4 is r to the 0, which, again, you really don't need or anything to the 0. It is just plain old 256. Now, if I had done this on the inside and said, isn't r to the 0 1? 4 times 1 is just plain old 4, and plain old 4 raised to the 4th power is still 256. Now, here I would almost distribute it first and then take each piece and figure out, so what's going on here? That negative tells me that I'm actually doing this, which means I'm actually doing that. And, you know, whether you take baby steps or you jump all at once, that's up to you. You know, if you can keep this stuff straight in your head, then more power to you. All right, more of this simplify following the rules of exponents. So we're going to say there's a 3 on top. And if I am subtracting like this, I'm going to go ahead and say -4 minus 3, that's -7. I'm going to write it first that way, and then I'm going to turn around and say, all right, if I want this as a positive exponent, then it's going to look like that. And the m to the -7 becomes an m to the +7 on the bottom of the fraction. Now I'm going to play the same game here. I'm going to have, so I'm going to have 2/3, and then I'm going to have x to the 4 minus 2. I'm going to have y to the -4 minus -3, minus -3. That's like +3. -4 plus 3 is y to the -1. And then here, -3 minus 4, that's -7, really. So now I'm going to have a 2 on top. I'm going to have an x squared on top. I'm going to have a 3 on the bottom, along with a y to the +1 on the bottom, and z to the 7 on the bottom. And that's about what my answer should look like. Now, same base method basically says if I have 5 to the this and 5 to the that, my bases are the same, which means that my exponents must also match. If the bases match, then the exponents are going to have to match one way or the other. So the rest becomes algebra. How do I solve for x to figure out how this works? Well, I have a -2x and a -1x. And when I think on the number line, I always want to pick on the little guy, which -2x is going to be farther down to the left than -x. So if I get rid of him, watch what happens. There's a reason that I pick on the little guy, because I wind up with a positive answer. That's just one less sign I have to keep up with, you know. There is method in my madness. So x is 3. We've solved the problem for x. If I were to go back up there and stick x, 3 for x, I would get 5 to the -3 on both sides, which it matches. Life is good. Now here's one where we can use the same base method, but only if you recognize that 243 is a multiple of 3. So once you start going down that road, you ask yourself, so what is 243 divided by 3? Well, that turns out to be 81. Oh, hello. 81 is an old friend. 9 times 9, which is 3 times 3 times 3 times 3. So how many 3's do I have here? 3 to the 1 is 3. 3 to the 2 is 9. 3 to the 3 is 27. 3 to the 4 is 81. 3 to the 5 is 243. So I could literally rewrite this as that equals 3 to the 5th. And now I have the same base. Now all I got to do is look at the exponents and say, hey, wait a minute, if that equals 5, and divide by -2, I get a -2 for the x. When I stick the -2 back up there in the problem, I wind up with 3 to the 5th on the left and 243 on the right, which is 3 to the 5th. Now here's one you got to think outside the box a little bit. What is one sure way to get an answer of 1? That is to raise something to 0. So does that mean that 1 could be the same thing as that? Oh yeah. Now I got my same bases, And 4 to the 0, which is 1, that means that 2x plus 3 equals 0, which means that I'm going to subtract the 3 and divide by 2, and x equals negative 1.5, or 3 over 2, however you want to leave your answer. I'm usually, I don't have a preference unless the directions are specific there. Now here, actually we're not using that this time, but I wanted to remind you because it will pop up pretty soon. That log of x is really log base 10 of x. If there's no base there, you presume that there's a 10 there. And natural log of x is the same thing as log base e of x, e being that number of 2 point something, like 2.17 or something like that. That is a mathematical constant that is involved in growth of life on Earth anyway. I don't know how it is on the stars, but now when they want you to rewrite them as logarithms, remember that as exponents, if a to the x equals b, then the log of base a, the base is still going to stay the base, but whatever that exponent is goes over there, which means that b must go there. And that's how I do it. I literally, here's the base, here's the exponent, and whoever's left over goes there. All right, so we're going to say log base x, and our exponent is going over there, which means our 17 is coming here. And here, I'm going to say log base 9, and my exponent is going over there, which means my x is going there. And then log of 15, my exponent is going over there, and b is going right there. Now, these are helpful. Sometimes you'll be faced with a problem like this, the log base 9 of x equals negative 9. But if I were to rewrite it this way, 9 to the negative 9 equals x, that's a calculator thing. I can punch that in a calculator and get an answer. So sometimes you have things in logarithms that can be written as exponentials and can be handled with a calculator. We're going to run into that situation with these last few also. If this is my base and this is my exponent, then I'm going to turn around and say x to the 2 equals 5. I'm going to turn around and say 7 to the 4 equals y. I'm going to turn around and say 3 to the w equals 8. Now, sometimes what will happen is that you'll be given a problem like this guy up here, log base x of 5 equals 2, and you can rewrite it here, and I can solve for x. I can take the square root of both sides, and that means that my x value is plus or minus the square root of 5. Now, here's a little heads up for you. Anytime that you go to the base of a logarithm like that and you try to plug a negative number in there, it is going to laugh at you. It does not like negative numbers in that base. So when I said that my answer was plus or minus the square root of 5, I could actually just ignore the negative value because it's not going to exist in the real world with logarithms. So positive square root of 5 would be my answer if I were solving this. Now, likewise, over on the right side, if I had a problem like this, 3 to the w equals 8, well, I know that 3 to the 1 equals 3, and 3 to the 2 equals 9, and so w must be somewhere between 1 and 2. And if I were to rewrite this in this fashion, this is a guy that we can punch in the calculator. Technically, we can say log of 8 divided by log of 3 and hit enter, so long as you got your parentheses going. Hit enter and you'll get a decimal for it, and that'll be whatever goes there. Life is good. So there is a reason that sometimes we switch back and forth between the languages, between exponential and logarithm. Okay, now that is the last of those, so that is the end of your notes.